Hi gang, in this video we are going to be doing section 3.8. This is higher derivatives. We're going to be talking about not only the first derivative but also the second derivative, what it means and how to interpret that. We will be going through the first page of our notes here. So it says here in the first question, it says, what do the derivatives mean? Given the first graph f of x, which represents a height of a hot air balloon graphed as a function of time, graph the first and second derivative and label each x and y axis to determine the meaning of each derivative. So what we have in this problem is a function f of x, which is equal to the height, and let's say measured in feet, and our x value, which will represent time, and let's just say that that's measured in seconds. And we're going to go over to our first graph here, which is our f of x graph. We have that one already drawn out for us. Labeling our x and our y axis. The x here is equal to seconds, and the y axis here is equal to feet. When we measure this graph, the slope of this graph, we need to remember that we will be calculating slope values at any given point. And remember that slope value there is the change in y over the change in x. And if we look at our graph, our y and x are measured in feet and seconds. So when we go to the next graph and we look at our first derivative, we will now be graphing a function that has an x value of seconds and a y value of feet per second. So when we graph this, remember, we think about a few things. We have a horizontal tangent up here, which translates to a spot on the x-axis, and we have another horizontal tangent over here, which is a spot on the x-axis, and then our graph is going up, and then our graph goes down, and then it goes back up, which translates into negative slopes, and then positive slopes, and then more negative slopes. So when we graph our function, it would look something like this. Now, this is my first derivative graph, which is measured in feet per second, which is what we call the velocity graph. Now, if we were to take this same graph and find slopes on this graph, remember again, that slope is measured in the change in y over the change in x, and my y is feet per second, and my x is seconds. So on my next graph, I will now be measuring a y-axis of feet per second squared in seconds. And we're going to take this derivative that we have here. I'm actually going to graph it in yellow. And then we would graph the derivative of that. And again, we have a place where we have a horizontal tangent, and then our graph is going up, and then our graph is going down. So when we graph the derivative of this, it will start positive and go negative. And that would be the graph of the second derivative. What does that second derivative stand for? Well, it's a graph of the feet per second squared, which we will interpret as acceleration. All right, so what do you need to know? You need to know that our first graph, where y is measured in feet, is a graph of our position. Our second graph, which is measured in feet per second, is the measurement of velocity. And our second derivative, our third graph, is a measurement of feet per second squared, which is a measurement of acceleration. Now let's take that in example 1 and figure out how to interpret that. Be with you in a sec. All right, for this graph, it says that we are going to now talk about the second derivative. The problem that we have says, given the graph of v of t, this is the first derivative or velocity graph. Sketch the graph of the acceleration, which is a graph of the slope values, and determine whether the velocity and acceleration are positive, negative, or 0, and at what values at the given values of t. And so I have a table set up here. At each of the x values, we're going to determine whether the velocity and acceleration graphs are positive or negative. I have gone and marked on my x and my y axis some values, just so that helps us keep things straight. We're going to start with my velocity graph, and I'm just looking at the values of this. And remember that everything below the x-axis is a negative number, and everything above the x-axis is a positive number. And we're just looking at where they are. When we look at these first values, up until we get to 2, we have positive values. And then at 2, it's negative, which is this spot right here. And then it becomes positive until we get to 7. Sorry, I said that wrong. We started out negative below the x-axis, and then it was positive until we get to 7, which is where it is 0 again. And then after 7, it drops below the x-axis, and we are back to negative. And so we fill in negative values. Now we're going to graph the acceleration graph. The acceleration graph, remember, is a graph of the slopes of the velocity graph. So when I look at my graph here, in this first section, I'm going to be measuring my slope values, and I choose a point, and I rise and run, so it goes up 2 over 1. This first section has a slope of positive 2. So we're going to fill in their positive values. And that goes until we get to 3, where we have no derivative value because of the corner that is there, where these two meet. This spot right here at 3 has no derivative. Then we have a slope of 0 until we get to 5. Where there is, again, no slope because of the corner. I did adjust this. Notice that this is no slope here and no slope at 5. Then my graph goes down. And again, we're just measuring slope values, rise and run. These are all negative slopes until we get to 9, where we have another corner. And then my slope is horizontal because it finishes off with that flat slope of 0 line. The first question here, and let's draw our derivative graph. We had first a slope of 2 until we got right there, which there was no slope. And then we have a slope of 0. And then we have a slope of down 2 over 2. So we have a slope of -1. Until we get to 9. And then we have a slope back at 0. So the red graph is a graph of my derivatives. Now, technically, at endpoints, we don't really have derivatives, so notice that we have open circles at both the beginning and the end of my derivative graph. And so that right there is the acceleration graph, which is y double prime. All right. This first question here says on the intervals, on what intervals is the object moving to the right or to the left? Moving to the left and to the right is looking at my velocity graph, and really we are just looking at the signs of this. When you move in the negative direction, it's moving left. When you move in the positive direction, it's moving to the right. So we can say that it's moving to the left on the interval from 0 to 2 and from 8 to 10, or if you prefer greater than less than notation, you could write it like that. Making a note here in my notes here, we're looking at negative velocity values. Then my graph is moving to the right when my derivative graph is positive, and that's in this section right here. So notice that it starts moving to the right when my derivative graph is above the x-axis. So we say that it's moving to the right from 2 all the way up to 7. Notice that we have round brackets there because at 2 and 7 it is not moving to the right. If you prefer your greater than, less than symbols, you can write it like that. And when we're looking at our graph, those are our positive velocity graph values. The last part here says, when is it stopped? And it is stopped when you change directions. So it stops at the places where it's equal to 0, and that would be at x equals 2 and at x equals 7. That happens when you have a change in the velocity sign from positive to negative or negative to positive. The last thing that we're going to talk about here is when is the object speeding up or slowing down. And we simply look at the graph for these values. An object is speeding up when the velocity and acceleration have the same sign. That means they're working together. It is slowing down when the velocity and acceleration have different signs. So when we look at our graph here, the easiest thing to see here is in this section right here at 6, where the velocity is positive and the acceleration is negative. What we're looking at on the graph is the velocity is above the x-axis, but the acceleration is going down. That is when it's working against each other, and that happens starting here at 5 and going until we have the number 7. Let me highlight that. That section right there is when your shape is slowing down when the two signs are working against each other. The other time that that happens is right in here from 2 to 3. Sorry, I said that wrong. Right here from 1 to 2, notice that my velocity values are below the x-axis and my acceleration is above the x-axis. If I look on my number line, it's in those two sections right there. When we go to our graph or our answer, we say that it's slowing down from 0 to 2. And actually, or 5 to 7. 0 to 2, 5 to 7. It is accelerating when they have the same sign, and that would be in this section right here, where the velocity graph is positive and the acceleration graph is both positive. Also, down here from 8 to 9, where the velocity graph is negative and the acceleration graph is also negative. We say that that happens from 2 to 3 and from 7 to 9. Sorry, I didn't get all that over there. There we go, 7 to 9, that section right there. All right. Hope that makes sense. We will talk more in class. Have a great night.